And now we're in chapter 4, which is applications of the derivative. So now we've learned all the fundamentals and the techniques of taking a derivative. Now we're going to apply those techniques, and we're going to see what can the derivative tell us about different situations and about graphs. So the first section we're going to look at is extrema on an interval. And extrema is just a generic term for looking at finding those maximums or minimums. Stock prices vary from day to day, making investments risky. How can we analyze the value of stock over time? And how could this help us make predictions for what will happen in the future? The value of Apple stock over a 14-day period can be modeled by A of t, where t represents the days after May 31st, and A of t is measured in dollars, and the graph of A of t is shown below. Pause the video and write down or describe what is happening with the value of stock over the 14-day period. We're just looking at the graph. What is the graph doing? It's decreasing on day 1, and then it's increasing to a max right here, about 217. And then it kind of does not a steady, but it does a decline all the way till we get to about day 13. And then there's a sharp increase again. Question number 2 basically asks us to just read this graph. What is the highest value of the stock during this time period? And what is the lowest value? So how high does this graph go? It starts at about $226. And how low does it go? Oh, right about $185 or so. Since these values are the highest and the lowest that it goes in the 14-day period, they're called the absolute maximum and the absolute minimum. It doesn't go any higher and it doesn't go any lower. Now for number 3, suppose you bought stock on June 1st. What was the highest value that your stock reached over the first week of owning it? And how does this value compare with your answer in question 2? Pause the video and write down your answer. Well, the highest it reaches if you buy stock on the June 1st, which is right here, the highest it reaches is right there, which is $217. This is not as high as the absolute max over the 14-day period, which we found was $226. Therefore, this is called a relative maximum. Question number 4, on which days is the value of the stock changing the fastest? How do you know? It's asking for a change. So when is it changing the fastest? Well, that's going to be when the slope is the steepest, which we can see happens on the 1st day and the 13th day. And then question number 5. For which values of t is the value of the stock not changing, and how do you know? So where on this picture is the stock not changing? Well, it's going to not be changing right here. Right here, it doesn't change. Right in there it doesn't change, and right in there it doesn't change. So at approximately 1.2, 3.7, looks like about 9, and a little bit before 13, so 12.7. And we know that the stock is not changing because the slope is 0. There's a horizontal tangent line. So these values, where the slope is 0, keep in mind the rate of change is 0. So that's why the stock is not changing. These values, where there is a horizontal tangent line, where the slope is 0, are called critical points. Well, we've got 3 main ideas. The EVT, the extreme value theorem, is an existence theorem. It doesn't tell what a value is, it just simply says that it does exist. So if a function is continuous on a closed interval a to b, then the function must attain a maximum and a minimum. In other words, if you have a closed interval and you have a continuous function, then there has to be a highest and a lowest value. This kind of makes some intuitive sense, right? There's an absolute maximum at x equals c if at x equals, when I plug in c, I get a bigger value than if I plug in any other value in that interval. So in other words, it's the highest value, highest y value that can come out of that function is at x equals c. That would be your absolute maximum. X equals c is a relative maximum if when you plug in c, it's bigger than all the values that are near it. So graphically, if you look at it, it's going to be a peak, but it's going to be bigger than any value near it, but not necessarily bigger than any value in the whole interval. Similarly, there's going to be an absolute minimum if, when I plug in c into the function, I get the smallest value of any other value of x that I can plug into that function. It's absolutely the smallest value. And finally, a relative minimum is going to be at c if, when I plug in c, it's the smallest value in that general vicinity. In other words, again, graphically, it's going to be at a valley on a graph. And finally, the third main topic of this section are critical points. And critical points are where the derivative is equal to 0 or undefined. Now let's check and see if we understand all this stuff. The graph of f prime is given below. For which x values does f of x have critical points? So keep in mind, this is the derivative value. So it has critical points where the derivative is equal to 0 or the derivative is undefined. So since this is the graph of the derivative, where is this derivative equal to 0? Is x equals 1 and x equals 3. And where is this graph undefined? It's undefined at 4. Because remember, in order for a function to have a derivative, to be defined, it has to have the limit from the left has to equal the limit from the right. So there has to be local linearity, and this point at x equals 4 does not have that. It's not because of the undefined point there, it's because the slope from the left and the right do not equal each other. Example number 2. Let g of x be 3x squared minus 8x plus 7.5. Find the critical points of g of x. Again, the critical points are where the derivative is 0 or undefined. This is a polynomial, so keep in mind a polynomial is never undefined. So we simply need to find the derivative and then set that derivative equal to 0 and find that value of x. So go ahead and do that. Pause the video, please, and do that. We get the derivative is 6x minus 8, setting that equal to 0. When we solve that, we get that x is 4/3. So a critical value is going to occur when x equals 4/3. Example number 3. Sketch a function on the interval from -3 to 8 that meets the following requirements. These are tough to do. I challenge you to do these. Pause the video and try to do what you can. Let's walk through this. First thing I did was I drew my interval, -3 to +8. There's an absolute maximum at the left endpoint. Keep in mind there are an infinite number of possibilities of graphs that could meet this. So the one that I'm drawing is not going to be the only one. I'm going to say my maximum is right there on my left endpoint. There's relative minimums at x equals -1 and x equals 3. So it just means that it's going to come, there's going to be a valley there. So at -1, I'm just going to draw a horizontal tangent line there. And then at 3, I'm going to draw another one right there. And there's an absolute minimum at 6. That just means that this has to be lower than any other minimum. So I'm just going to draw it lower than any other minimum. And it's undefined at x equals 4. So it probably is going to have some sort of cusp at 4. So I'm going to draw this part like this. It's only got to go to 8, so we can keep it there. And then it's got to have a minimum there. And it's got to have a minimum there. And it's going to go up there. So that could be a graph. This would be a little bit smoother here. That doesn't look super smooth. So as long as this is a cusp, because remember the derivative, the slope from the left and the right is not the same, and the rest of it is a smooth graph, we've met all those requirements. Number 4, the function f of x is continuous on the closed interval -2 to 1 and differentiable on the same open interval. If f of -2 is -5 and f of 1 is 4, which of the following statements will be false? Let's prove instead which ones are true. There exists a c in that interval such that f of c is equal to 0. Well, since c is between that, in that interval, since 0 is also between their corresponding y values, this is true by the intermediate value theorem, which remember we learned back in chapter 2, I believe it was. Letter B, there exists a c, again in that same interval, such that the derivative is equal to 0. Well, again, according to the mean value theorem, the derivative would be, we could guarantee that the derivative is equal to 0 if the average rate of change is equal to 0. So let's go ahead and find the average rate of change. Pause the video and find the average rate of change, please. Well, we found that the average rate of change is 3, so we can't guarantee that this one is true. So this one we know is false. There exists a c in that interval such that f of c is equal to 3. Again, this is the same as part A, since 3 is between -5 and 4. We can say that this is true by the intermediate value theorem. Part D, there exists a c again in that interval such that the instantaneous rate of change of the derivative is equal to 3. Well, back up here in B, we found that the average rate of change was 3. So since my instant rate of change equals my average rate of change, they're both 3, we can say that this one is true. This is true by the mean value theorem. And then finally, there exists a c again in that interval such that f of c is greater than f of x for all x in that interval. Again, this is true because the directions tell us that the function is continuous. So by the extreme value theorem, since the function is continuous, there has to be a maximum. So there has to be a value f of c that's bigger than all the rest of them. If there's any questions on this, please make sure you come to class and ask them.